Hello, this is Baugh again. Today we'll be covering the Lecture 1 notes. This recording is originally made in for the fall of 2015 semester for CIS 2353 Data Structures with Java. I've created these lecture notes such that it will cover 3 chapters of largely review material prior to diving into the more heavy material. And this largely condenses the information that are found on the slides that come with the Collins book. So we'll be going off of these lecture notes today. I strongly recommend you review the chapters as well. You may gain further insight that way, but also my lecture notes should prove useful and as a good outline. So the coverage for this lecture will be the following. This is your first week's worth of information that you should review. Review of Java programming language in general, object-oriented concepts, and additional features of programming and Java. The topic checklist for Chapter 0, you have primitive types classes, which include the string class. What does the equality operator versus the equals method, how are they different, how are they similar? Local variables, what are they? And the scanner class, these are very commonly used classes and things that are associated with classes. We'll also talk about arrays. We'll also talk about methods, arguments, and parameters, and also about output formatting. For Chapter 1, we will talk about data abstraction. We'll talk about abstract methods, which you should have some idea what these are from your Java 1 and 2 experience. But we will go a little bit deeper with these and do a review as well. Also interfaces, which have some similarities with abstract classes, and the methods inside of an interface are all abstract, so understanding abstract methods will help you understand interfaces better. We will also talk about the 3 pillars of object-oriented programming, because Chapter 1 is focused largely on object-oriented programming. So the 3 pillars are encapsulation, inheritance, and polymorphism. We'll also do provide some brief information about UML class diagrams as well. Further, in Chapter 2, we'll talk about static variables. We'll talk about constants, methods again, in a little more detail. We'll do a little bit of JUnit, exception handling, including checked versus unchecked exceptions, file output, system testing, the JVM, which is the Java Virtual Machine. We'll talk about packages and also discuss overriding the equals method. So, Chapter 0 topics. Before we go too deep into the object-oriented topics, we need to review the basics of the Java programming language. Even if you think you know Java really well, you should pay close attention to this chapter, because it could help you review some very, very important details that you may not have picked up the first time around or never gone back to revisit. So often you'll learn a whole lot revisiting topics that you think you're very well versed in because you know them well, and then when you go back they can sometimes seem more meaningful. If you're rusty in Java, this is also a perfect time for review. If you're confident in Java, then this may be a good time to solidify your understanding of terminology and concepts, perhaps even from a different perspective or with different examples that you wouldn't have considered yourself. So first of all, I want to make sure that you have Eclipse installed or an IDE of your choice. I recommend downloading Eclipse. This particular version that I'm using is Luna. So it's fairly easy. It's not quite as straightforward as JGrasp, but this is industry level. It's not just a teaching tool. This is an industry environment. You just go to File, New Java Project to start out, and then you'll be given a source folder over in the Package Explorer over here. And we'll be able to create source files very easily there and run them and view the output near the bottom, or it'll pop up if it's a GUI application. So first of all, primitive types. Primitive types are fundamental built-in types in Java. They're also known as base types. In Java, there are 8 of these types. You should memorize these 8. You should know that they're available. If I say, what are the primitive types in Java, say on a test or an assignment of some sort, you shouldn't even need to look in notes or anything. You should know these like the back of your hand. So you've got the integral types, which are these four right here. The integer, which is 4 bytes. Longs are 8 bytes. Shorts are 2 bytes. And bytes are, not surprisingly, 1 byte. But these can all store integer data. Then you've got the two real types, which are double and float. Doubles are 8 bytes, which is 64 bits, and floats are 4 bytes. You have char, which is 4 bytes, and then you have boolean, which are 1 byte. At some point, essentially everything we do in Java will rely on these 8 base types. You should be able to name them all and their sizes if asked what they are on an exam or homework assignment. So memorize these. The integral types are actually pretty easy to memorize if you're careful. If you can remember that a byte is a byte, and then that it goes in the order byte, short, int, long, then you can easily remember byte is 1 byte, short is twice that much, so it's 2 bytes, an int is twice that much, which is 4 bytes, and then a long is twice that much, which is 8 bytes. Then double and float, you just have to memorize are 4 and 8, because a double is twice as much as a float, so if you can remember what a float is, it's not that hard to remember how much a double contains. You'll also have to memorize that a char is 4 bytes and a boolean. Boolean, you only really need a bit, but since a byte is the smallest addressable piece of memory on computer architecture, we have to occupy a byte. Okay, so it's the same size as a byte data type. Classes. As a brief review of classes, a class acts as a blueprint for objects. Okay, so class is like the blueprint, object is like the actual thing that you create from the class. If you consider, for example, a vehicle, a car, you don't drive the blueprint, obviously. You drive the actual car built from the blueprint or the schematics. The class is just the set of schematics. The objects are the instances of the class. The class consists of fields and methods, and it describes what an object of that particular type looks like and does. Now there is some special stuff that you'll need to learn regarding classes that kind of breaks this idea about classes versus objects, which includes the static methods and static fields. But in general, if we're talking about creating an object, we're talking about creating an actual instance or a particular thing out of that class, which is the blueprint. So fields contain data about the objects. These are the values or attributes that describe the object. And the methods are the behaviors of the object. What does the object do? Here's an example. This right here is a counter class and its client. I've displayed the counter class itself. It's fairly simple. A lot of the things that you'll be doing will involve creating a fairly simple class. You've got a private field named count, so private int count. Variable names often and most frequently start with lowercase letters. The methods will sometimes start with capital letters. Classes, definitely you should start with capital letters. This particular method is a constructor. This constructor sets the count to 0. It's not technically necessary because all fields are set to 0, but we're just showing you that it could do something. Then we have an overloaded constructor, or what we call a parameterized constructor. This particular constructor has the same name as the class, just like any constructor, but it takes a parameter. This is an initial value we want to set the count to. If we were to repeat all this in Eclipse, this is one way we could do it. You could go to File, New, Java Project, and we're going to call this project Week 1. I'm going to hit Finish. Give it a few seconds. And you'll notice if you expand the little project tab here, you've got an SRC folder. When you right-click that, go to New, you can select Class. For this one, I'm going to create the counter class that we're dealing with right now. Alright, so I get my code here. You can give it a package name. In this case, I'll just use the default package because it's a little more simple, even though it discourages that. Let's see what we can do. We want to do private int count and then do a default constructor. So inside of here, private int count. This is our private field. Then you're going to have a constructor here. This is the default or no arg constructor because it doesn't have any arguments. We'll set count to 0 in here. Now this is technically not necessary. Public counter, int, I'll just call it init val. We're going to set the counter equal to the initial value that the user wants to set it to. An interesting note about constructors is that if you do not provide any constructors, in order for the class to create an object or an object to be created from the class, there has to be a constructor. So the compiler will actually provide you with one. It will provide you one with no arguments. That's called the default constructor. Most computer scientists refer to any no argument constructor as the default constructor. But some literature will refer to this, if you explicitly write it, they'll call it the no arg constructor, and they'll just call the one generated by the compiler the default constructor. I tend to call it the default constructor if it has any kind of if it has no parameters, whether you write it or whether the compiler generates it for you. I generally tend to call it the default constructor. However, you can write other types of constructors. This one right here is a parameterized constructor. And then this one would be the default constructor. Default or no arg constructor. Now, you notice I use the term CTOR here, C-T-O-R. You will see that in literature a lot as a shorthand for the constructor. So keep that in mind. Another interesting aspect about constructors is that, let's say I provide this one here, the one with the argument, but I don't write this one. Let's say I never typed this one. I can delete it and pretend it's not there. Does the compiler now still provide one with no arguments? The answer is no. Once you provide any constructor whatsoever, the compiler no longer provides one. So you have to be very, very careful with that. Just be aware of that. Okay. So you've got I called it a init value. Doesn't really matter what you call the parameter name. Then they have an accessor or getter for the counter to determine what the counter is. So let's do this. Public, and then the return type is an int because that's the type of count. And we'll say get count. Call it that. We're just returning the counter. Pretty straightforward. The next thing we have is we don't allow the user to set the counter directly. That would be called a setter or a mutator method. But we do not have a set count, so there's no, besides the initialization with the overloaded constructor here, there's no way to initialize counter to a different value or set counter to a different value. But we do have an increment, and then we have an overloaded version of increment, which increases the amount by a specified amount. So let's do increment and then the overloaded increment, and then there's a reset which sets it back to 0. So here we go. Public void. We'll say increment. You could also call it increase. Increment just increases it by 1. So I'm just going to say count plus plus. And then we're going to say increment, so it has the same exact name. And I'm going to call the parameter, call the argument amount. And then we're going to say count plus equals amount. Equivalently, you could say count equals count plus amount. All right, that's equivalent. And then you have reset. Public void reset. All this does is set count to 0. So that's pretty straightforward. That's counter.java. So we have an integer variable named count. Whenever you have any variable that is in the scope and is not static, any private field that lives inside the class, it will be automatically initialized to its 0 value. And then objects will be initialized automatically to null. We call these, since they are not static, they actually, every copy of this counter, anytime we create a counter, it will get a copy of count here, its own copy, and one counter might have a different count than another. we say that they all get the same copy, and they're called instance variables. Instance variables, because they belong to the specific instance. We have the accessor method that I showed you, and then the increment and the two different increment methods. We've got the overloading used there, and then we've got the reset method, which sets the value of count back to 0. So let's write a client to actually use this counter. So I'm going to close counter.java. I'm going to create a new one. We'll call it counter client. It doesn't really matter what we call it. Public static void main string args, and let's see if I like what we did here. Okay, yeah, all right. So counter C. I could just, I guess, copy and paste this stuff just to save a little bit of time here, if it works, and it does. All right. So I'm gonna space it out just a little bit more. Okay, counter E. There we go. All right, so we have counter C. This is us declaring a reference variable. Now we have to be very, very careful. This does not create a counter object. The object does not exist at this point. This declares a reference variable, which means that this variable, which in and of itself has its own memory, has memory designated to it that can hold a memory address of a counter. That's what its purpose is. Since it's a reference variable, its purpose is to hold a memory address or a reference to an actual object. So this is not the object. Although we might refer to the object C, a very, very important technical difference is that this is the reference variable, but the actual object is pointed to or referenced by the address inside of C. Now at this point there's nothing. So in the next line we have C equals new counter. Now anytime you see the keyword new, that means that it is about to reserve memory at runtime, not compile time. That's why we call that dynamic memory allocation. When you declare an integer or a primitive type, for example, the memory is allocated at compile time. That's static compilation. Now don't get that confused with the static keyword. There are differences. But we call that or static memory allocation right here is at compile time. Dynamic memory allocation is when you see the new keyword. So that means that the memory is actually reserved on a special area of memory called the heap. Notice that once this variable gets a counter object, the equals symbol just causes this reference variable to point to or to contain the memory address of the counter that was just created in memory. Then we call increment, which is a method of the counter class, so that will cause whatever values in here, which will be 0 to start off with because we use the no arg constructor, right? There's no argument here. So if we go back here and look at our class definition, the counter is 0. Now we didn't have to do this because it's an instance field, right? So it would automatically be 0, but this is just for clarification purposes. If we go back here, it'll start at 0. Then we'll increment it to 1, and then we call the overloaded version of the increment method to increment it by 5, so it'll be 6 at that point. Then we take a temp variable, grab the counter, and then say what the counter value is. We create another counter. This one sets the initial value to 10, right? So this calls this constructor right here. So once that's done, then we call increment, so it should be 11. Get the value. We actually create another counter here, and then we point to D. Now notice, again, when I say counter E or counter D or counter C, that none of these creates an actual counter object. All they do is hold addresses. So when I say counter E equals D, that does not create a brand new counter object. All it does is it copies the memory address of D into E. So that means E and D are both pointing to the exact same object. Exact same object. So if I say temp equals E.getCount, print it out, and then increment E, that will also affect D automatically because they both point to the same object. Any method that I call using this reference variable will cause there to be an effect on both of the the single object that is referenced by both of these reference variables. So if I run this, this is the output I get. Counter is currently 6, which is what we expect for our counter C up here. Counter E is currently 11, right, because it was 10 originally. It was 11. We pointed to the same object, got the counter, and printed it out. So that should be 11. And then we increment it by 5, and then we'll see that now that is 16. All right, pretty cool. Everything seems to be working. This shows you the output. The client of the class is fairly straightforward. We declare the reference variable named C. That's where we started. And we kept going. Remember that that does not create an instance of counter. You just declare a variable to point to a specific type. Okay. When you assign when you assign the value of D to E, that does not copy the object. That causes the address to be copied. So this is actually what's happening in memory. Here's our counter object living on the heap, also called the free store. They both contain the same memory address. So if the memory address is FF2233, that means that E and D will both contain FF2233. Now, point 3, arrays. An array is a collection of contiguous elements in memory. Just like any variable, an array has an identifier or a name. However, instead of referencing one value in memory, an array can be accessed can access multiple locations. These little locations that can contain values inside the array are actually called cells. The values that live in those cells are called elements. You could think of it as an apartment building as a good analogy. The array could be the apartment building. It has a single name, okay, single variable name. Chestnut apartments, oak apartments, what have you. But they have multiple elements living at the different indices. So the elements are like the tenants. We're going to keep it simple and pretend there's one tenant per apartment unit. So elements, tenants, live at the different indices, which are the apartment units. And note, language-wise, singular of indices is index. Some people say indexes, but indices is an older term, and it's used generally more often. So here's an example. I'm not going to retype this in the compiler. You should be able to very simply. We didn't even create a separate class. Notice this is a segment, because there is a class outside. So you'll notice that we create an array. You do dynamically allocate the memory for it. So this allocates memory. This creates the reference variable. We're doing it on one single line here. Since it has these brackets right here, bracket notation indicates this is an array, not just a simple integer. And then when you say equals new int 5, that causes there to be 5 cells created to hold elements. Then we're going through here and looping, then printing the array afterwards. So then it shows you the result of printing the array. So most of this should be pretty straightforward. If you're not comfortable with arrays, I strongly recommend you review the chapters involving arrays in the Gaddis book or even just in the Collins book. If you have any problems with arrays or need more clarification, don't hesitate to email me. I will try to see maybe if I can provide more information for you. Further, we're going to talk about arguments and parameters, which have to do with methods. So with methods, which are named blocks of code that you can call over and over again, the terms argument and parameter are often used interchangeably, but there is technically, again, a difference. Remember we talked earlier about parameterized constructors. So argument and parameter, those terms are used a lot. The argument to a method, it is what is used when the method is called. It's either a literal value, such as John, if it's a string, so integer literal like 5, double literal like 12.5, or a variable, my num, the name, age, etc. The parameter is used in the heading of the method. So it's technically just a local variable of the method, and it serves as a placeholder for whatever value is sent in as the argument. So it receives that value and basically acts as an alias for that value locally to the method. So if I have main here, and I put a string here, I love pandas, and then I also call this method print backwards, John Baugh, my name is Bob, and then pass some string. I'm showing you two different ways to do it with three different calls. This method gets called here with the string John Baugh, so we'll print it out backwards because it calls print backwards right here. This is a string literal John Baugh in double quotes. It is an argument to this method call. It's an argument to the method. So is my string is Bob, and so is some string which contains the value I love pandas. These are all arguments. Okay, they're not technically parameters. You could call them actual parameters too. That's another term for them, but typically we say argument for that, and you say parameter for this little placeholder down here. When I call this first one, for instance, John Baugh, the string value, is stored in word, which is a local variable to this method. So this method uses word, takes the length of the word -1, starts at that, goes until we're at 0, and then prints the word out starting at the last character, and then decrements I, goes down to the end. So that means it's starting at the H, and then prints out the G, then the U, then the A, then the B, then the space, then the N, then the H, then the O, then the J. Right? So and here are your printouts for these different things. You've got the John Baugh, my name is Bob, and I love pandas. Right? Printed out backwards. So the parameter of the methods is in the header, right above the body of print backwards. So that is the parameter. It is a local variable to this method, and it serves as a placeholder for when values are passed in as arguments. So when this is called, it calls this method, but it puts that value of the argument inside of word to be used locally here. So because ahead of time we don't know what the user might use, so we just have to have a placeholder. That's why we would just call it word, because we know it's supposed to be a word or a phrase that's printed backwards. That's all we know. All right, output formatting. There are many ways to format output in Java. You've probably used printf at very least, but another way is with decimal format. So if you're printing directly to the console, frequently printf will be used, and so a lot of times with GUI applications, decimal format will be used. This example is fairly self-explanatory. So in decimal format objects, use the 0 as a placeholder to indicate that if a decimal exists in that digit, display it, but if none exists, display a 0. And then use the number symbol, which we'll see in a second, like down here. It means if a decimal exists in the digit, display it, but if none exists, display nothing. Okay, so it's a little bit similar. But then you have all these arbitrary precision doubles here. You've got one with, the number pi to 5 digits. But you notice that it's going to print them based on the formatter that was used rather than the what's actually in the value right here. Okay, it has to do with using the formatters. I'll let you play around with that. Make sure you're reasonably comfortable with it. So that was the Chapter 0 topics. Now let's dive into the Chapter 1 topics. So this covers some basic object-oriented concepts. The first one is data abstraction. It's a very, very important concept, especially from a design standpoint, with object-oriented programming. The user of a class is interested in what a class provides. So if I'm the client of the class, okay, there's a class provided for me to, for example, interact with an engine or interact with a character in a video game that I'm trying to control. I don't care about the details. Someone else programmed that. So what I'm going to do, or what I want to do, is know what the class provides. This is called the specifications. What does the class do? I don't care how it does it. I'm just the user of this class. Now I might be a developer for another class. I'm using your class to develop another class maybe. So I don't have to worry about the details of your class, or it might even be a class I wrote long, long ago, but I don't have to constantly be thinking about it. So as the user, I'm concerned with what the class provides, not how it does it. However, the developer of a specific class is focused on how the class is implemented. So that's called the implementation. So you've got specifications, which is what the class provides, what it does. No details about how it does it, don't care. But as the developer of a class, I am focused on how the class is implemented, how it does what it does. This separation of the what from the how is called data or implementation abstraction. Okay, we generally just use the term data abstraction. The user of a class shouldn't have to rely on the implementation details of that class. This is a very, very well-known object-oriented software engineering principle called the principle of data abstraction. Abstract method. So an abstract method is a method that doesn't have an implementation. Now that sounds kind of strange, but you might think, well, why is that? Why do we even need that? It can be declared in an abstract class in which some, but not necessarily all, methods are not fully defined in the superclass. This is useful in situations where the developer of a class wishes to allow the subclasses to perform specific implementations, or provide rather specific implementations of the abstract methods. Therefore, you as the superclass do not provide the implementation. We've talked about abstract classes in previous courses, or you should have. An abstract class is one that has the abstract keyword in its header. So public abstract class, abstract test 1. This means that I can never say something like abstract test 1a equals new abstract test. I can never create an instance of an abstract class. They are used for the purpose of simply providing a superclass for other classes to implement. Now, they can provide concrete implementations, like right here. I have an abstract class, but it does have a concrete implementation here of do something. Now, the classes that inherit from this or extend abstract class 1 can override do something. Java uses what's called dynamic binding, which we'll talk about a little bit later. Dynamic binding means that at runtime is when a call to a method is associated with the actual definition of that method. So right here, it waits until runtime. Some languages like C++ use static binding by default, so they need special syntax to tell the compiler, hey, wait until you run this to determine which method you're calling, which function you're calling in C++. But in Java, we don't have to worry about that. We have this right here. We have a definition here, and we have dynamic binding, so that means when we call this, it'll automatically determine, based on the object it points to, which method it should be calling. However, this abstract class right here also has an abstract method. So it has one concrete method right here, and this one in turn strangely calls the abstract method, so that's interesting. But you also have an abstract method with the abstract keyword after public on the method. Notice that there's no body, there's just a semicolon. That's because this class does not define how does some abstract method work. There's no definition. That's left up to the inheriting classes. So the abstract class has a concrete method and an abstract method. You can never do this. Like I said before, you can never do this because it's a compiler error. Since abstract test 1 is abstract, you can't create an instance of it. However, if it has a concrete non-abstract subclass, say concrete class 1 that uses the extends keyword with abstract test 1 and implements some abstract method, then that class can be instantiated. Keep this in mind when we discuss polymorphism shortly. The next related topic is interfaces. Interfaces are similar to classes, except they can contain only constant fields using the final keyword and public abstract methods. Now, you don't technically have to provide these keywords. It's automatically assumed in an interface, and there's no other way you can have it. You can't have private methods in an interface. You just have public methods. They are public abstract. So that means if a class uses the keyword implements with a particular interface now, similar to abstract classes, It's kind of like an abstract class with all abstract method. Any method inside this interface is public abstract. It's automatic. You don't have to specify any other way. So you could provide it, the definition this way, but the second syntax is more obvious because it is unnecessary to provide these keywords here, public abstract. You can use the implements keyword instead of extends with interfaces. So you use extends with classes and use implements with interfaces. You can have more than one interface that a class implements. However, you can only inherit, extend, at most one class. So, Java does not support multiple class inheritance like some languages like C++. It does, however, support multiple interface implementation. So, the next thing are the three pillars of object-oriented programming. So you should be at least remotely familiar with these concepts. First is encapsulation, then we'll talk about inheritance, then polymorphism. Classes give us the ability to combine attributes, which are the fields, and behaviors, which are the methods. So attributes and behaviors. This is what classes give us the ability to do. We combine these things into single entities. This is often described as putting the attributes and the behaviors into a capsule and treating them as a single unit, the object, right? So because we put them into this single unit, we are putting them into like a capsule. We call it encapsulation, creating a capsule, encapsulation. So when you couple fields with methods, it's called encapsulation. So this typically allows us to create things like private fields and protect the actual implementation from the outside world. The details of the data and implementation is hidden. Technically, the hiding of data is called information hiding, and the hiding of the implementation, not surprisingly, is called implementation hiding. But typically, the term information hiding is used for both, the protection of the data and the protection of the implementation, how it's implemented. So inheritance is the second pillar of object-oriented programming. Inheritance is where we use the extends keyword, or in the case of interfaces, the implements keyword. Inheritance is the characteristic of a programming language that allows us to create a new class based on another class. This is a form of software reuse. The newly created class, in Java we typically say that the newly created class from the subclass is called, or from the superclass is called the subclass. In some terminology you will see the term derived class or child class. But in Java we typically use the term subclass for the class that's doing the extending. So class A, or public class A, extends class B, okay, or extends B. It absorbs the characteristics, behaviors, and attributes of the older class, known as the superclass, base class, or the parent class. So typically in Java we'll use the term superclass. Furthermore, the third pillar of object-oriented programming, so we have encapsulation, putting things into a capsule. We've got inheritance, which basically means we can extend the capabilities of a single class or various classes or multiple interfaces. And now we've got polymorphism. This is often the least understood. There are even a lot of professional developers who don't fully understand polymorphism. So it relies on inheritance, though. If you use a reference variable, remember, reference variables versus objects, there's a difference. Reference variable is the variable type, and the object is the type that follows the keyword new. So if you use a reference variable of type abstract test1, that's okay. But you can't, if it's abstract, you can't say abstract test1 equals new abstract test1. That's illegal if it's abstract, right? However, if you use a reference variable of that type, and then you create an object of one of its children or child types, subclasses, you can do this. This is part of the magic of polymorphism. So I can say abstract test1 sum var equals new concrete class 1. Since concrete class 1 is a form of an abstract class, then that's okay. Since concrete 1 is an abstract class because of inheritance, you can do this. So if I have, for example, a base class, we can think of this as animal, and we can think of a specific animal like dog. Okay, so dog is an animal. In this case, we're saying concrete class 1 is a general name, is an abstract test1, or it's of that type. Okay, so because it inherits from it. A dog inherits the characteristics of an animal. Cat inherits the characteristics of an animal, right? So because of inheritance, we can do this. However, we cannot create an instance of abstract test1 if it's abstract, right? So we can use the abstract test1 reference variable. Remember, this does not create an object. We're not violating the rule that you can't create an object of an abstract class because we're not creating an instance. We're just creating a reference variable that can point to something that is an abstract or inherits from abstract test1. In this case, we actually create the object concrete class 1. So, for further understanding, let's assume that I have a concrete method. Testing stuff declared in both the abstract superclass and the concrete base class thusly. So let's say that I have in the superclass abstract test1, I have this. It's very simple. It just prints out in the abstract superclass. In the derived class, oh, that's messed up. This should actually say in the derived class. Okay, so I apologize. So that should say subclass. So let's assume that a client creates an instance of the concrete class 1 and stores it in an abstract test1 variable as we did earlier. Then they call testing stuff on the variable, which implementation is actually called, in other words, what's printed. So even though I goofed here, this should say in the concrete class right here. This one does say in the abstract superclass. So the question is, which one, the definition inside of the base class or the derived class, in other words, the superclass or the subclass, which one is called? If I create the variable as the abstract, but the object as concrete class, which one's called? Is concrete class's version of that method called, or is abstract test1's version called? The answer is it will call the concrete class's implementation because it waits until runtime to determine what method definition to bind to. This is called dynamic binding. This is part of polymorphism. So this is different from binding the method name to the method implementation at compile time, which is called static binding. Java does dynamic binding by default. The testing stuff method, called a virtual method in some languages, is called. So the testing stuff method from the subclass is called, right? The concrete class. That's the version that's called. Okay, very quick overview of UML. I'm going to let you read most of this on your own, but just notice a couple things. UML, or Unified Modeling Language, is a set of various diagrams to model real-world or potential systems. It allows people, even those with little or no programming, as well as those who are very experienced, to communicate the high-level ideas about how systems go together. One of the most common or popular types is called the UML class diagram. This is how we describe at a high level classes. So and they're actually language independent for the most part. So if you describe a UML class, I could send it to my Visual Basic friend, or my Java friend, my C# friend, my C++ friend, and they could all use that and implement a class based on the diagram. So here are things to remember: the symbols in UML and the levels in what we would say most object-oriented languages. So Java, for example, the plus symbol is for public, minus symbols for private, and then the pound sign is used for protected. Other things you should memorize, or at least be familiar with: if you have a line with an empty arrow inside, this is called generalization in UML. It represents inheritance. So I would say something like the dog would be on this side, and the animal would be on this side, because dog is an animal. So the arrow, again, the arrowhead points to the super class, okay, or the base class. Aggregation is represented by an empty diamond. So the unfilled diamond is attached to the containing class. It's a type of association, but it's stronger than just a basic association. It just means basically there is a containing class. For example, the company contains a list of employees. Right here we have an array list of type employee. Since it contains instances of that, we would say this is an aggregation, so that's why there's a diamond. However, there are different types of employees. Notice there's not a full implementation shown here, or a full specification shown here, but we do have the triangle here, right? So you can tell that the company contains or has an employee, rather a list of employees as members. Okay, so what do we got now? Chapter 2 topics. So we've gone over Chapter 0, Chapter 1, Chapter 2. This chapter covers even more features of the Java programming language. So first of all, static variables. You should be familiar with static variables because we talked about instance variables. These are fields that are associated with a specific instance of a class. In other words, an object. So when you create an object, we talked earlier about the counter class. When you create an object, each of these counter objects get their own copy of count. These are instance variables. However, inside of some classes, you might have static members of the class. So static variables are associated with the class itself. You don't have to have an instance of the class in order to access it. So for example, I might create a public variable here. This is possible. This is a static field, and I'm setting the value at 15. Later on, I might say my class name, if this is created in something called my class name. You use the name of the class rather than a specific object, and then you can call that member directly. Constants are another type of variable that you should be aware of. It seems weird to say that a variable is a constant because they can't vary, but in general, in computer programming languages, we say that a variable is just a named location in memory. A constant is simply a variable that can't change. You can't change once it's given a value. Some languages use a keyword const, like C++, C#, etc., but Java uses the keyword final. In terms of a variable, this makes it constant. So final int my constant equals 120. Later on, I can never say my constant equals 240 or change it. This is a convention, but not required, that you name the constant. Usually, with variables, we use what's called camel case. You start with lowercase and then, so my pet camel or my pet horse, whatever, you would start with lowercase, and then every time you got to a new word, you can't have spaces in identifiers, so obviously you would just capitalize the next letter, do the rest of the word, capitalize the next letter, so it looks like the humps of a camel. But you don't use camel case usually with constants. Use an older convention, which involves all capital letters, and then underscores between words, since camel case is not an option here. This is a convention. It's a way in which something is frequently done rather than a language requirement. I could create a constant and have it all lowercase. I could use camel case. I could do whatever I want. However, it is a convention. When most programmers will look at a variable and they will see that there are all caps and then underscores in it, they will most likely think that this all caps case indicates that that is a constant. So they can look through the code and say, oh, that's probably a constant, without even seeing the declaration. That's a convention. Methods. Now, we've talked about methods before when we talked about parameters and arguments, but here's a little more formal definition. A method is a reusable block of code with a name or identifier, just like variables have identifiers. They talk in the book about correctness of methods. So a method is considered correct if it satisfies the method specification. In other words, the method is correct if it does what it says it should do. Since we've briefly reviewed methods already, I won't spend too much time doing that, but just be aware of that. So you can often take large problems and break them down into smaller, more manageable chunks. You can solve those little chunks of problems with little collections of algorithms or smaller collection algorithms called methods. These are little sub-programs or sub-processes, subroutines that Java can call over and over again on these chunks to see if they can solve them or to solve them. In Java, we call these methods. Some languages use other terms, procedures, functions, subroutines, etc. JUnit. Now, JUnit is testing software. Each method in a project is considered a unit, and the J stands for, not surprisingly, Java. JUnit allows methods in a class to be tested in a systematic manner and without human interaction. As a simple example, let's consider that we want to ensure a particular class employee has a getSalary method that produces an expected output. So, you can put the @test annotation before the method name, and that will mark it as a test method. Notice that that method will in turn call the method being tested. Okay, so we have to be careful with that. You must use the import org.junit.star among other import ports. However, you also need to ensure that the JUnit library is available to the project. In Eclipse, you can simply select Fix Project Setup. So I would click this right here, Fix Project Setup. In Eclipse, once you hover over these, if it doesn't recognize one of these, you hover that, go to Fix Project Setup. It will add the library. So let's take a look at an example. We've got getSalary of an employee class, and then later on we have a JUnit testing class. We want to test getSalary. This is how it's actually being used. Notice you're not explicitly calling test getSalary, you just put the test annotation in front. And then notice in main, all I'm doing is calling run classes. And then I pass it this JUnit testing class, which is this thing, .class. Then it will print out the results, result.getRunCount, get failures. It will tell you information. You get all sorts of information from it. But this is one of the tests. So it's called test getSalary. That's one of the tests that will be run automatically. If you have more methods with a test annotation, those will be called too. Note that @test goes before your methods that are explicitly for the purpose of testing something else. So we have this. We have possible diff. So this is for a possible difference, give or take $5. We have employee equals new employee. Double expected is 50,000, so $50,000. Then you call assert equals. You've got expected employee.getSalary, comma possible difference. So give or take $5, this employee that you're calling it on should be making $50,000. So it's just giving you an indication of what happened. So this employee, if you goof, it'll say it failed, or it'll give you a list of failures. It'll give you a run. There's no failures here, so it's good. However, if you put double expected 90,000 and the employee is only making 50, then it will tell you, hey, I ran a test, but hey, I got a failed test here. I called it in the JUnit testing class. I expected 90,000, but it was 50,000. So it's incredibly useful. It says what the expected value was and what the return value was. So I was expecting this, and I got that. So it's telling you when stuff failed. So I would highly recommend at least looking over the JUnit stuff, become familiar with it. Exception handling, we should go over this. You should have learned it when you were in Java 2, at least, a little bit. So an exception is an object. Don't lose sight of that fact. An exception is an object. It's created when something goes wrong in a program. However, an exception is not just any object. When an exception object is created, the flow of control is halted, and the exception is thrown. The exception that is thrown is ultimately caught by some other segment of code. So when we don't have a program crash and instead fail gracefully, this is called making the program more robust. Robust programs may have to fail, quit, or otherwise stop the current executing process, but it's important that we try to significantly reduce the probability that the bugs will cause a fatal runtime error, or what most people in common parlance call a crash. When a program fails but doesn't crash and instead is handled in a robust fashion, we say that the program fails gracefully. Here's an example of an exception being handled within a method. So if I call doStuff from main, and then I have this method doStuff, I have an array here, and I have a try-catch section. Here's the syntax for exception handling. You have the try block, which contains the potentially dangerous code that could crash. Then you have the catch block, which says, oh, if that happened, here's what we do. So in this case, this is actually dangerous, and it's going to break because we're saying start at 0, go up to the value 4, so less than 5. But that's going to crash because really in this array, even though it's size 4, that means it has valid indices 0, 1, 2, and 3. So if it ever tries to read area 4, index 4, it's going to crash. That's exactly what we get when we output. Note that if a particular method doesn't handle an exception itself, it can propagate the exception by using the throw keyword. So you can throw new illegal argument exception, for example. Now, you need to understand the difference between checked and unchecked exceptions. Most exceptions in Java are checked exceptions. This means that the compiler checks that either the exception is caught within the method or that a throws clause with an S this time, notice it's different than this keyword, not the same thing, throws clause is added. So what we mean by added is appended to the end of the method heading. So for example, public void sample checked. If I have some code in here that could throw an IO exception, I better have the code throw, or the clause here throws IO exception at the end. So in this case, the heading indicates that the method could produce an IO exception. This is a checked exception. In fact, all exception, except those that are subtypes of runtime class exception, right here, or errors aren't either, but anything that is, except those that are subtypes of runtime exception, are checked exceptions. So notice under runtime exception you have things like null pointer exception, or arithmetic exception, index out of bounds, etc. The reason these are not checked is because they can pretty easily be corrected with good programming techniques rather than using exception handling. For example, array index out of bounds exception and index out of bounds in general, no such element, null pointers. You should be checking this stuff with if statements and things like that. Don't let the array go out of bounds. That was probably some dumb thing on your part. So anything under error and anything in the runtime exception, any of these things are unchecked, but the stuff such as IO exception, you won't know if you can read a file or if you have specific input problems until runtime. So those are checked exceptions. The compiler will complain if you do not handle or propagate the exception. As a note, this figure 1.3 here is from Didle and Didle. That is not the book we're using for the class, but it is a very, very good book. If you are really, really wanting to have a really good reference material for the class and also for Java in general, I would highly, highly recommend getting a book by Didle and Didle. So that's the shameless plug there. All right, I am not getting reimbursed for that, unfortunately. So there are two subclasses of throwable. One's exception, from which all the exceptions derive, and the other's error, where you find errors that are typically you just can't catch them because they aren't usually caused by your code. So if the Java virtual machine sets itself on fire or blows up, or you run out of memory on the system, or it's something that you could not have possibly known through your or corrected or recovered from in your own code, the thread dies, the AWT dies, there's an error in the virtual machine itself. These are things you can't do anything about, so they're unchecked exceptions. Also anything that derives from runtime exception is unchecked. So runtime exception, those are the ones that you can usually fix with good coding practice. So what about file output? You should be familiar with file input using scanner, and then there's file output as well. You can output data to a file using the printWriter class. This is one way to output to the file. In order to use this class, you must import java.io.star. So import that so you can have access to the printWriter class here. So for example, I could say printWriter pw equals new printWriter, and then pass it directly the name of the file that I want to write to. Then you just use, just like system.out object that prints to the screen, you can use the printLine method with the printWriter. So it works the same. Make sure to close it when you're done. I'll let you read the thing on system testing, but I'll go down to the Java virtual machine here. Java virtual machine, also called the JVM, is a virtual, so it's software emulated or simulated computer. As far as the JVM is concerned, its machine code is Java bytecode. So you know that all kinds of different machines, Macintosh, or Apple computer, a PC, Linux boxes, all these different things running on, or the software running on all kinds of different hardware. You got RISC processors and Intel processors, AMD, etc., etc. Many of these have similar, but not always identical, machine code that they understand. But a RISC processor and an AMD processor won't understand the same language. Um, so the Java virtual machine is a very, very clever way. It, as far as it's concerned, is a computer. It's a simulated computer, and you can think of the top of it as being the same on all the platforms. So that's why Java is platform independent. It'll run the same on any machine you're on as long as it's capable of running Java and supported. But the bottom half, you can think of, not really a half, but the bottom of that quote unquote machine actually does what it has to do to interact with the native environment on that particular machine. So it translates what it needs to into the actual machine code on the system. But Java bytecode is portable. When you compile a Java application, it does not turn into native code typically on a particular platform. It turns into Java bytecode. And then this is the machine code for the JVM. So that's why it's portable, and therefore it's machine independent. JVM does many things, but one of its duties is that it initializes fields just prior to their invocation. So if you have instance fields specifically, instance variables, they're initialized to 0 value, so 0 for integer, 0.0 for double, double quote for string, and null for other classes. Also, the JVM performs automatic garbage collection. This is because when you use new, the new keyword, the memory has to be deallocated at some point. So the JVM takes care of this for you most of the time. In some languages, like C++, you have to do it manually. You have to use a delete keyword in C++ to say, oh, I'm done with this memory now. Otherwise, you'll get what's called a memory leak. Okay, these are far less likely in Java because of automatic garbage collection. You should be familiar with the concept of packages. In Java, a package is a collection of classes that are related or at least grouped in an organized fashion. If you want a class to belong to a specific package, you have to put the package declaration at the top, so package keyword. And usually we use what's called reverse DNS notation or reverse URL notation. It looks like a website. You don't have to own the website, but it looks like a website backwards, so com.jpbaugh.mathlibrary. So that would be a package. In much of the software, they will it'll automatically generate a folder structure. So we have a COM folder, then a JPBaugh folder underneath, then a math library folder underneath, and then inside there, you will get a specific class of some sort. Later on, if you want to use it in another class and it's not in the same project, you would have to import it. So import com.jpbaugh.mathlibrary. And then the name of the class, so calculator. So overrides the equals method. So how do you override the equals method? Equals method's inherited from object, which all classes either directly or indirectly inherit from or extend. If you have a class and you do not use the extends keyword after it, in other words, you're not explicitly doing inheritance, the class will automatically inherit from object. So the compiler will automatically cause it to inherit from object. So directly or indirectly, your class inherits from object. Equals is one of the methods that is inherited. So if I have two people, then I could say p1 dot equals p2. Now, so I have to determine what does it mean for two people to be equal, okay, people objects. So in this case, we're going to say if the first name and last name are equal and their weights are equal, then I return true, otherwise return false. So notice I'm using the override annotation, not technically required, but is useful. And it's used in typically later versions of the Java. I would recommend using it anyway. So you have equals, Equals, again, since it's an inherited from object, it receives an object as its parameter. So you cast O to a person type here, and then you look at the, oh, I don't know, I called that, yeah, other person here. So I've got other person here. This is the casting, just to keep it, this is the casting right here that's done. You cast it, the object, to a person, and then you're storing it in this reference variable. Remember, it's a reference variable. You're not creating a new object here. You're pointing to the same memory location and just specifying that it is a person rather than just some generic object or some other type of object. Then you compare the other person. If their first and last are equal, and then the weight is equal, then you return true. Otherwise, you return false. This is our user here. Notice that we have John Smith and two different people. We are creating them as two different objects, but you will notice that their data is the same. The one in the middle, P2, is not the same. So you will end up with P1 doesn't equal P2, but P1 does equal P3. See? So it's very, very interesting. Equals is also used on strings, so keep that in mind. It's automatically implemented for strings to determine if the strings contain the same value. That's why we were able to use this. You might think, well, what the crap, we're using equals method again here. Well, that's because first, in this case, in the person class, a first is a string, and so is last. So I have to call dot equals. If I use the equals equals, or the equality operator, that's going to, excuse me, excuse me, that's going to compare the memory addresses, which may or may not be the same. In this case, I can use equals equals because this is a primitive. Primitive types, you can use the double equals operator and compare them because primitives will just say yes or no. There's no equals method for primitives because they don't inherit from object. All right, so hopefully this has been informative and a good review. Please, most lectures will be somewhere in this range. They could be anywhere from 30 minutes to, 2 hours or something. It kind of depends. But note that it is a 4 credit hour class. So if you you need to do more, put in more effort yourself, definitely. Read through here, type out the examples, and run them. Make sure you're comfortable with them with any clips. If you don't do that, I guarantee you're going to have problems. I've witnessed it over and over before in various areas. So just make sure that you do what you're supposed to do, and you'll be good. If you have any questions, please contact me, jpbaugh at oaklandcc.edu. And have a great day. Thanks.